Hi everyone. Closed loop idle control is one of those things that makes an engine really behave nicely and have a car that's really nice to drive. So because I'm fussy, we're going to talk about that. Now first of all, the ECU needs to know whether or not to go into closed loop idle control. I've explained this in other places, but I'll explain it again here so it's all in the one place for people. Now it's not enough to know that the throttle's closed. I'll give you an example of when that would not work. If you're at say 2000 RPM with your foot off the throttle, driving along, coming to a stop sign, then if the ECU were to go into closed loop idle in this condition, then it would say, well, we're idling too high, we're at 2000 RPM when our target's 800, and it would try to close the idle valve. This isn't going to make any change to the engine RPM because the engine's being driven by the car. So the ECU keeps pulling idle duty cycle out until you get to the stop sign, you put your foot on the clutch and the engine stalls. So this is what's called integrated wind-up, and we don't like it and we try to avoid it. So the ECU really needs to know when the engine's idling. That's really the issue. When is it the case that the idle control valve is what's determining the actual RPM? So the first requirement for this is that the engine has to be disconnected from the wheels. Now, some manufacturers like Mazda and Nissan have a neutral switch on the gearbox and a clutch switch on the pedal. So whenever either of these is true, then the ECU is disconnected from the wheels and the ECU can go into closed loop idle mode. Now, some manufacturers don't have these, but instead they have a vehicle speed input, and on those cars, the ECU will only go into closed loop idle if the vehicle is stopped. Now the modular ECU will go into closed loop idle in either of these conditions, but the throttle has to be closed and the RPM needs to have fallen close to the target idle RPM. Or if it hasn't got to near the target idle RPM, then it has to have been in this condition for a certain amount of time. So for example, if you do a free rev up to 6000 RPM or something, and you take your foot off the pedal, then the ECU can't go into closed loop idle straight away because it would say we're idling too high when not actually idling at all, we're just waiting for the RPM to come back down. So we need to set this value in the neutral timeout setting, and that needs to be enough time for the engine to come back from maximum RPM with the throttle closed to idle. So a value of say 5 seconds or so would be a good place to start. Now in addition, the throttle closed flag has to be working. Now you can see this on the throttle position sensor input page. You can see what the threshold is below which the ECU will consider the throttle to be closed, and you can also see when it thinks the throttle is closed. So that has to be working correctly as well. Now let's look at some of the other settings required. The first thing we need to do is enable closed loop idle. Now secondly, we need to have our target idle speed table configured correctly. Now the target idle speed can be changed based on whether air conditioner is active, thermofans are active and that sort of thing, but we need to have the basic values set in the table as well. Now we also need to make sure that our closed loop conditions are set correctly. So if we have a neutral and a clutch switch, then those two can both be connected into the ECU, and both of them can be configured as digital inputs, and then those digital inputs should both be set as clutch. Now functionally they mean the same thing, which is that the engine's not connected to the wheels. So what you could do if you wanted to is actually wire them both to the same input, and that way when either one triggers, the ECU will know that the engine's not connected to the wheels and we can go into closed loop idle. Now if you don't have those, then you'll need to have a working vehicle speed sensor input, and there's another article on wheel speed inputs which describes how to configure that. Now one other thing to check is that the closed throttle flag is reliably working correctly. Sometimes people put on aftermarket throttle bodies and they get sticky, the machining tolerances aren't all that good, and they don't actually go back to the same position each time you take your foot off the pedal. So if that's the case and it sits at 2% instead of 0%, and you've set your closed throttle percentage to be 1%, then it won't go into closed loop idle in that condition. Now, in this case, the thing to do would be to fix the throttle body, of course. If you can't do that, then you at least need to set the minimum throttle percentage to a higher value so that it always gets there. Now, the last settings that we need to set are the PID gains. Now, I did a whole talk at PRI in 2016 on PID control and how to set those gains. So I'm not going to describe PID here, but some starting values, say 1, 2 and 0.15 on Mazda engines for PID in that order, and about 252 on Nissan RB engines. So when the ECU goes into closed loop idle, you can see that it's done this, and you can see the percentage of idle effort that comes from the closed loop component. So it might be positive or negative, depending on whether it was too high or too low. Now the other thing I'm going to say is that the modular ECU actually has two stages of closed loop idle. The main stage, which I've just described, but it also has a pre-stage, if you like, where only the derivative term is calculated. And the point of this is to help the engine come back down to idle nicely. So this first stage is activated as soon as you take your foot off the throttle and the other closed loop conditions are met. So either the clutch or neutral switch is depressed or the vehicle is stationary. And you can see this has happened because that idle derivative flag comes up. So if you watch these flags as you do a free rev, you'll see that the idle derivative flag comes up as soon as you take your foot off the throttle, but then the closed loop idle only comes on when the engine has got back down to idle speed. Now in this condition, the ECU still calculates the PID control parameters, but it only outputs the derivative term. So this helps the engine come back down to idle nicely. Now this can help with mitigating dips or stalls on return to idle, but of course the fuel map has to be correct on the way back down to idle as well. So if you have a problem with dip or stall coming down to idle, then firstly make sure this idle derivative is enabled. Secondly, you may want to try increasing the derivative gain of the PID settings. And what's going to limit how high you can increase that is when it starts to hunt or oscillate at idle. Now, generally with idle control, try to get most of it done with the proportional term if you can. Just have the integral to clear up the steady state error. This is on solenoid valves. On stepper motor control, normally you only use the integral term and no proportional, no derivative. The reason being that they're so slow to act that you can't really move them, otherwise they'd just be banging back and forward between steps all the time. You can increase the integral term as high as you can, and you're going to be limited by a slow hunt that occurs when it's too high. Now, the last part I'm going to discuss is ignition timing at idle. So the default operation of the ECU is that it uses the main ignition map in the idle condition, just as with any other condition, but when the ECU is in closed loop idle, it can adjust the ignition timing to stabilize the idle speed. Now to do this, a separate ignition timing table for zero throttle is deselected, and the idle ignition table is a table of the ignition timing change as a function of the RPM error. So RPM error is defined as the actual RPM minus the target RPM. So for example, plus 200 means that you're 200 RPM above the target. So in general, you'd have about, say, plus 10 degrees at minus 200 RPM and minus 10 degrees at 200 RPM, and interpolated in between, and that really tends to help stabilize the idle speed, deal with little idle hunts and that sort of thing. I haven't yet found an engine which didn't benefit from having idle ignition control. Now, another method which has been requested by one of our customers is to have a separate closed throttle ignition table. So instead of just configuring it in the map based on the timing that you want, the ECU looks at this separate idle ignition map when the throttle's closed. Now in this case, you can choose whether the time is dependent on the RPM error or the actual RPM. And then this table, instead of being a correction to the main ignition map, actually becomes your ignition timing. Now, the main problems that you're going to encounter when setting up closed loop idle control, the main one's going to be an idle hunt. Now, in this case, the first thing you should do is confirm that it is actually due to the idle control. So often idle hunts are caused by a rich lean hunt in the fuel map. So to test this, you can set the PID gains all to 0, and if the hunt remains, then it's not to do with the idle control closed loop. It must be due to the fuel map or ignition map or something else. Now, if the hunt goes away when you set the PID to 0, then it is actually being caused by the closed loop idle control. And one thing you can do is increase the derivative gain. If that makes it worse, then you'll need to decrease it again and then decrease the proportional and the integral gain terms. Or another way of looking at it is that with PID being 000, if there's no hunt, and the PID being whatever you've got them set to, there is a hunt, then the point where you've got good control but without the hunt must be somewhere in between those two if it exists. Now, the other problem, which I sort of mentioned before, is getting a dip or a stall on return to idle. Now, for this problem, actually could be caused by several causes. The most likely one that I've seen in practice is that the fuel map is just not tuned properly on the way back down to idle. But if you look at a log and you see that the idle effort is reducing when it's come back down to idle before it's actually got to idle, and it's in closed loop in that situation, then that means that your neutral timeout is too short. It's going into closed loop before we've got back down to our target idle speed, and therefore it's pulling out idle effort. Now, the other thing that you can get wrong is having the ECU going to closed loop idle control when it shouldn't be, such as when you're driving. And the way you can tell this is, of course, with a log file. You can also look at the closed loop idle percentage component while you're driving along and see if that or not while you're driving, but in the log you can review what it was when you were driving, and you can see if that's changing, and if it is, then that means that it must be in closed loop at the time. So that means that you need to look at your closed loop conditions properly to see if you've got working vehicle speed or if the neutral or clutch switches are being triggered when they shouldn't be. Thank you very much.